Okay, so today what I've done is I've provided guided notes for you in a Google Doc that I'll share with Google Classroom over sections 8.4 and 8.5. So hopefully this helps with what we're going to be working on this week. So these are the notes for section 8.4 on binomial probability. So binomial, remember that word means that there's two terms, there's two things occurring. So, with that said, when we have a binomial experiment, it's an experiment where there are two possible outcomes, either success and failure. We also know in a binomial experiment that we will know how many times we are repeating this experiment over and over and over again. It's a fixed number. And then with that, each trial that we run every time as we're repeating this over and over and over again, the trials are independent. What that means again is that one doesn't affect the other. So, for example, flipping a coin is considered a binomial experiment. Every time I flip a coin, we have two possibilities, heads or tails. We flip it 100 times, I fix the number of trials, and every time I flip a coin, the outcome is independent. One coin flip doesn't affect the next coin flip. So each time we flip a coin, the probability of success remains the same for each trial, nothing changes. So if we're able to meet all three of those conditions for a binomial experiment, then we can calculate a binomial probability. So calculating the binomial probability is where we do that for a single trial. In order to do that, we have to know two things. We have to know how many successes and how many failures there are, so a fixed number. And we have to know the probability of success and the probability of failure, and each trial has to be independent. If we meet all three of these for a binomial experiment, we can calculate a binomial probability as the probability of X successes in trials is equal to the combination of n choose comma x times the probability of success to the x number of times power times 1 minus the probability of n minus x power. So that's our formula. We're going to use that to calculate binomial probabilities. So, for example, you are told that the chance that an American falls asleep with the TV on at least 3 nights a week is 1/4. Suppose a researcher selects 5 Americans at random and is interested in the probability that all 3 are TV sleepers. Okay? Or not all 3, just 3. Okay, so here we go. So, first things first, we know that our N is 5. That's how many that we're choosing from. And our X is equal to how many we want here, so that's 3. And we know that the probability of a success, which in this case is being a TV sleeper, is 1/4. Okay. So now, using this, we can use our formula to calculate that the probability of X being equal to 3, the number of TV sleepers, is equal to the combination of 5 choose 3 times our probability, and I'm going to go ahead and just write this as 0.25. So 0.25 to the third power times 1 minus 0.25 to the 5 minus 3 power. So this would be the combination of 5 choose 3 times 0.25 to the third power times 0.75 to the second power. Now, why is it this way? Well, because 0.25 is the probability of being a TV watcher, we will add to know that for 3 people. The probability of not being a TV watcher is 0.75 then, and that would be the case for the 2 people that we're looking for. So now, here, we use our handy dandy calculator to calculate NCR. So I'm going to use my graphing calculator to do that. So we know that here, the combination of 5 pick 3, that's 10, times 0.25 to the third power times 0.75 to the third power. When we do that calculation, we end up with 0.0879. We're going to round out to 4 decimal places. So the probability of choosing 3 that are TV sleepers out of this sample of 5 would be around 9%. Not very good. Okay. So in our next example, this time we find that a recent survey found that 59% of college students attend more than one institution during their college career. Suppose a sample of 6 students is chosen, assuming each student's college attendance pattern is independent of the others. Find the probability that exactly 3 of the 6 students attend more than one institution. Okay, wonderful. So we could do this. Well, we have to know NN and P, NX, and the probability. So in this case, we know that the recent survey found 59%. That's our probability, so we're going to use 0.59. Our sample, our N, is 6, and we want to know 3. Okay, wonderful. So, to calculate the probability of 3 out of 6, we do the combination of 6 choose 3 times 0.59 to the, third power times 1 minus 0.59 to the 6 minus 3 power. Okay? So the combination of 6 choose 3, that's 20, times 0.59 to the third power, times 0.41 to the third power, is equal to approximately 0.2831. So that would be our probability. And again, notice I rounded to 4 decimal places. Okay, now, this time, what if it's none? Okay, so we're going to use the same N and the same P, but this time our X changes to 0. So it'd be the probability of 0 out of 6. So that's the combination of 6 choose 0 times 0.59 to the 0 power times 0.41 to the 6th power. So 6 choose 0, that's 1. Well, 0.59 is 0 power, that's 1. And it would be 0.41 to the 6th power. So when we do that calculation, we end up with 0 0.0048. Very low probability of choosing a sample of 6 students, and none of them have attended more than one institution. So again, another example of how we can calculate binomial probability. All right, flip the page. So this time we're going to go back to the coin example. So this time you're told to find the probability of getting exactly 7 heads and 8 tosses of a fair coin. So again, things we need to know. We need to know N, we need to know X, and we need to know P. How many tosses are we doing? We're doing 8. How many are we looking for? 7. What's the probability of getting heads? 0.5 on a fair coin. So the probability of 7 heads in 8 tosses is equal to the combination of 8 choose 7 times the probability of getting heads to the x power times 1 minus the probability of not getting heads to the 8 minus 7 power. Well, the combination of 8 choose 7, that's 8, to the 0.5 to the 7th power times 0.5 to the first power. So then when we calculate that, we end up with 0.0313. So there's a 0.0313 probability of getting 7 heads and 8 tosses. All right. Another example of where this can be used is when we talk about defective items. We're looking at manufacturing processes. So we look at a selection of items for a sample. We look at them being independent, and that the probability of any one item being defective is 0.1. So they're asking us to calculate the following. Okay, so the probability of one defective item in a sample of 15. Well, again, we need to know N, we need to know X, and we need to know P. So N, the number of trials, that's 15. We're looking for one defective item, so X is equal to 1. And the probability of that one item being defective is 0.01. So the probability of one defect in 15 items is going to be equal to the combination of 15 choose 1 times the probability of 0.01 to the first power times the probability of 1 minus 0.01, the probability of not choosing the defective item, to the 15 minus 1 power. So the combination of 15 pick 1, that's 15, times 0.01 to the first power times 0.99 to the 14th power. So then when we calculate that, we end up with 0.1303. So there's a 13% chance, a 0.1303 probability of picking one defective item in a sample of 15. Okay. So now the next question says, what's the probability of at most one defective item in a random sample of 15? Okay, so again, this at most. So because it says at most, this time this means 0 or 1. 0 or 1. So keep in mind it's an or. So what does that mean? Well, we have to find the probability of 0 plus the probability of 1. We already know the probability of 1. That's the 0.1303. So now we have to find the probability of 0. So the probability of 0 is going to be the combination of 15 pick 0 times 0.01 to the 0 power times 0.99 to the 15th power. Well, this just ends up being 1 times 0.99 to the 15th power. So when we do that calculation, we end up with 0.08601. So the probability of at most 1 would be equal to 0.08601 plus 0.1303, which gives us a probability of 0.9904. So there's a 99% chance of you picking at most one defective item in a random sample of 15. Okay. Now, last example of where this can be chosen, of this here where there's multiples. So if we have a 9-person jury where each member acts independently of each other and makes the correct determination of guilt or innocence, we assign a probability of 0.65. We want to ask, what's the probability that the majority of jurors will reach a correct verdict? Okay. So we need to know our N, we need to know our X, and we need to know our P. Well, we already know our P, that's 0.65. We know our N, that's 9. X, on the other hand, well, notice because it says a majority. So more than half. So what's at least the majority of jurors in a 9-person jury? Well, that would be anything greater than or equal to 5. So in this case, our X is going to be anything greater than or equal to 5. Okay, well, that could be 5, that could be 6, that could be 7, that could be 8, that could be 9. So if I want a probability of X is greater than or equal to 5, well, I've got to do all those. So I have to find the probability of 5, plus the probability of 6, plus the probability of 7, plus the probability of 8, plus the probability of 9. Okay. So I'm going to use my formula to set this up. So we find the combination of 9 choose 5 times 0.65 to the 5th power times 0.35 to the 4th, plus the combination of 9 choose 6 times 0.65 to the 6th power times 0.35 to the 3rd power, plus the combination of 9 choose 7 times 0.65 to the 7th power times 0.35 to the 2nd, plus the combination of 9 choose 8 times 0.65 to the 8th power times 0.35 to the 1st, plus the combination of 9 choose 9 times 0.65 to the 9th power, or to the 9th power, yep, times 0.35 to the 0 power. Yay us. Okay, so after we do the calculation, we end up with 0.2194 plus 0.2716 plus 0.2162 plus 0.1004 plus 0.0207. So when I add all those together, we end up with a probability of 0.8283. So there's about an 83% chance of the majority of a jury reaching a correct verdict. Okay, so I'm going to go ahead and stop here. Again, if you have any questions about this, please feel free to reach out to me, send me an email, we can set up a Google Meet, and we can go from there. So this concludes section 8.4. Thanks for listening and have a great day.